Hello, hello. How is everyone? Welcome to class 9 about reverse engineering. Is the internet on? Everyone is connected or? Okay. So, today's class is going to be about reverse engineering. I'm happy to be the one giving it. Yes, let me make it a little bit bigger. You are right. Thank you, Martin. Let me close this. Is it? I can do a bit more, but okay. Thank you. I hope you have access to the document and everything. This class is going to be a little bit more continuing from Martin's class last week, but I will try to refresh some of the concepts that we've seen. But it has a little bit of a different focus, so you don't need to remember the exploitation, but you will see a little bit of assembly, a little bit of C, and we'll see how it goes. If you have any questions at any point, just stop me and ask, please, because I know that the topic can be a little bit convoluted, it can be a little bit tricky sometimes, or maybe I don't explain something well, so please ask me and I will be happy to oblige. So, the results from the last class survey, around 3/4 of the people said that it was okay, and for some people it was a bit too fast. We understand. I hope the pace today will be good enough. Again, please stop me if I go too fast. Parish notices no Pioneer prizes yet because we didn't have any assignments the past 2 weeks, but we're going to have an assignment today. For the mock students, please start your class 9 Docker now because it takes some time, so you don't have to wait and lose track. And if any of you has not installed IDA free yet, please do before the second hour, because the first part of the class we're not going to use it, but you need to have it for the second part, and it may take a bit of time. They added some licensing, so it may take you a little bit of time to do it. So if you start it in an hour, you're gonna get lost. So please. So we're going to talk a little bit about what is reverse engineering, very little theory, and then we're going to do some preparations about GDB and a little bit of what kind of things we are looking at in the debugger and in general prepare ourselves. And then we're going to do 2 main topics. One is we're going to be reversing a network protocol, and then we're going to reverse a C binary, an C executable basically that was created from C. So what is reverse engineering? Does anyone have any definitions? As always, we have cookies. We have the official cookie thrower and chocolate thrower. So does anyone have any idea or any definition? What is reverse engineering to you when you hear it?
Trying to figure out the original code from already compiled.
Thank you.
Trying to figure out the original code from the already compiled result or executable, whatever is the final result.
Okay, close, but is it only about code?
That I don't know.
Oh. The system, what it does to input to happen to the output.
Okay, so given some input, we have some output, and we try to figure out what the system does.
Yes.
So it's a black box, you would say.
Yes.
So which is the same for the code, but it could be any system. Maybe you want to reverse engineer how your clock works, or the old people that were taking these old televisions with the big tubes, and they would try to figure out how they were working. And that's also reverse engineering, because nobody is giving you the blueprints or tells you exactly how it is. But in our class and the security context, a lot of the time is about code. It can be malicious code, it can be firmware, it can be different types of things, and we don't have access to the source, it's a black box, and we try to using some tools, looking at the assembly or looking at the internals and try to figure out what is happening. But as we can see, it will also be about networking and we can reverse protocols. Because maybe we don't have the specification, but we want to understand how the protocol is working for our own reasons. In the context of the code, we have the forward process, for example. So we design the code, we write it, we compile it, if it's a compiled language, we fix bugs, we recompile, we test it, we fix more bugs, and eventually we end up with some some code that runs somewhere. When we go to the reverse engineer, we go the other way. We disassemble, so we have, let's say, a binary that's an executable. We disassemble to the assembly language, and then we can try to do decompilation to something that looks like the original C code, and we'll see how that looks. And we need also a lot of thinking to understand what the things we see, what exactly are they doing, because the process is not one-to-one. You may not recover fully what you had in the start. And a lot of guessing is required, and a lot of hypothesis and testing and trying to figure out what exactly is happening. So why do we need it in general? In security, why would we need to do any reversing? Do we need it? Why do we even talk about it? I mean.
So I guess usually when we have a system, it does something, but there's a very high chance it also does something it's not supposed to. And it's much easier to figure out the unintended ways which can later be used to abuse them, from understanding how it works rather than just trying all the possible inputs and seeing if something breaks. So understanding how it works inside can be used to figure out the weaknesses and then craft exploits based on that. Okay, that's one definition. In general, I would say also when it comes to malware, if you have like something that you know it's malicious, someone infected a computer, and we have access to the malware that is running on the computer, we may see some of the actions, but maybe we want to actually understand more details about what it does. So as Max was saying, you want to go in and see what it does. For the malware, we may want to see how they spread. We may want to see how they communicate, and sometimes they may be hard-coded IP addresses or other indicators, and we want to create some threat detection based on the information that we see inside the binary. So malware analysts do a lot of reversing to figure out both what the malware is doing, but also how to make it easy to detect. So they get some specific things that are very specific to this specific, I said specific 3 times, to this malware, and then they create rules to be able to catch it faster and all that. But if we don't talk about security, are other people doing kind of reversing for any reason? Do you know any other cases? Maintenance. Pirate software, yes, good. Other one. So we have maintenance, pirate software. Exactly, steal information from the competition. It's okay. So, I don't know, product kind of information. Yes, one use case that you probably already know, and it's close to the pirate software, is the gaming community. So all these cheats and the things that everyone trying to do are the cheating, and they don't, to try to create things to win in the games. There is a huge community of reverse engineers that have nothing to do with security, but they're about gaming, and they want to hack games and be able to win and sell their cheats and all that. So it's not about security malware. Anyone can do reverse engineering, and also it's about curiosity. And it's a big discussion. Let's say I buy a device, I buy some hardware, and I don't have specifications. Do I own it? Am I allowed to look into it and see how it works? Am I allowed to modify it? And maybe I'm curious, I want to see how the Wi-Fi is connected and what kind of card it uses. And the manufacturer doesn't want to tell me. But I open it and look at it. So I'm, in a way, try to find the specifications, how it works, because I'm curious. It's mine. I want to do something else. Maybe I want to connect it somewhere else that I'm not allowed. And again, it's a big discussion about the right to repair and the right to actually, do you own your hardware? Do you own your software? How far deep can you go? Can you modify? Maybe you understand it, but are you allowed to modify stuff? Big discussion. So just to motivate a little bit, there was I don't know if you, have you seen the story about the hacking the DRM on the Polish trains? So for our people that maybe on the internet they haven't heard, we heard because Poland is quite close to us. In 2022, there was a company that they sold trains to the Polish, I don't know, railways, and Then the Polish Railways wanted to, when they do the service, they wanted to outsource it, and they created like a tender, and some companies bid and said, who is gonna service the trains? And another company, other companies won. And they found out that when they were trying to service the trains, that under certain conditions, the trains stopped working. And the conditions were very, very, very weird. So one of them actually called this ethical hacker group called Dragon Sector from Poland. And they said, okay, something weird is happening. Can you help us trying to figure out why the train stopped working? Like, we tried to fix everything. We serviced everything, we tested everything, and the train doesn't move. So the hackers got the firmware from the train and reverse engineer and found out that there were some logic bombs or lockup mechanisms that were triggered under conditions. For example, geofencing. If the train was in an area close to where the other service providers were, after some hours it stopped working. If the train was stopped for a number of days, which means it was serviced, it stopped working. And not only that, so they found the logic bombs, but also they found that if you press specific buttons in the cabin of the driver, you could unlock it. So this company was charging extra money for fixing the trains. They were saying, oh, you don't know what you're doing. Let us fix it. Pay us to do it. They would go, they would pay thousands of euros, and they would just press some combination of buttons, and poof, the train works. So these hackers, they provide the solution, they explain how it works, and they also gave 2 beautiful talks in the Chaos Communication Congress. We put the links in the footnotes, I think. Yeah. Yes. So if you're interested, it's a very good story. So the first one was how they did it, and the second was the aftermath, because then there was lawsuits. The company said, oh, you hacked our trains, and now they're not safe to drive. There were parliamentary investigations in Poland, because this is not exactly legal what the company was doing. You cannot just lock people's trains because you want to make more money. So it was a very, very interesting discussion, but this is the beauty of reverse engineering and how they managed to actually fix a problem that shouldn't have happened in the first place, in my opinion. So if you're interested, we have 2 links. You can hear the talks. They're very, very interesting. Well, they did very nice stuff, and I think it's easy to follow. So, any comments or questions? Any from the internet? No. So let me see. So when we do analysis of reverse engineering and analysis of the binary files, we have 2 major ways, or there are 3, but 2 other major ways that we're doing the analysis. The first is static. So you take the binary and you decompile it, you get the assembly, and without executing it, you just try to understand what it does by just looking at it. And it can be by looking at the imports, the strings, the binary itself, the assembly, and it's kind of safe because you never run it, so you don't have any malware running anywhere. Then there is a dynamic analysis where you run the malware into some sandbox, hopefully, or a virtual machine. You try to see the behavior, like does it send anything in the network? Does it change any files on the system? Does it do anything in the memory? And sometimes malware can detect that they are being monitored and they change the techniques, but usually you need both kind of approaches. It's not that you can only do it with static. Sometimes you need to run the malware to see the behavior, to trigger to get some information. But the dynamic analysis, you need to make sure you run it in a sandbox because it may be dangerous. Yeah, as for tooling, there are a million tools, but we're not going to use all of them. Just to give you an idea, there are different disassemblers and decompilers. We're going to use IDA, but there are others that are also kind of open source, like Ghidra from NSA, Radare, which is more command line. It's very powerful, but a little bit steep to learn. There are GUIs, there are other companies like Binary Ninja, and so on. In Linux, we also have a number of tools that we can use besides the disassembly. Like Linux has a lot of commands that we can run to see information. And if you're working on Windows, in order to avoid installing all the tools, you can go and click and get the Flare virtual machine, which has scripts to download all the tools. We are going to be doing Linux only, so we're not going to go there at all. We're going to use only IDA free and a little bit of GDB. So Are we ready to go? Let's do it. So in your host computers, please go and download this pickup file from here. I have a link. Oh, I didn't know it's not big. Okay, so we should have put it. It will take a little bit of time, but it's 100 megabytes. So this file is from a communication of a RAT, a remote access Trojan, that was running on an Android phone. So Camila was a researcher in our lab. She was doing her thesis. So she installed it in some Android emulator, and it has a command and control server, and you will see some communication between the Android malware and the communication. We'll try to analyze the protocol that they are using, and we'll try to see what kind of commands they're sending and all that. So please install it, and then open it with your WireSag. I will do it also. Okay, and to help you a little bit, I will tell you that we need to filter and see only the packets that go to port 8000. So I will give you a few minutes to do that and try to see on your own before we start any analysis if you can find anything, and if you see anything interesting or if you have any observations. So just use the filter, it's on the document as well, and only I'm telling you that this is the communication protocol between the phone, the RAT running on the phone, and the computer. So take a minute or two and try to see what's happening. Oh, I need water. I know it sounds a bit arbitrary, but if you were doing it from scratch without anyone telling you, you would be faced with that. So do you have any ideas where to start, or if you saw something that sparked your interest? Or it's okay if you didn't, but yeah. I know it's not easy in a minute to find a lot of things, but yeah. Anything? All good. Okay, I'll put your attention in the first packet that has this PSH, the push flag bit. Or is it correspond? Let me go a little bit up. And we'll see that among other things, okay, we see the TCP and the IP and all the headers and everything, and we see that it has some data. So we'll start from there. Okay, and if you see on the right side here, so we see the hex dump, how the bytes are looking, the raw bytes, and then we see their ASCII representation on the right. And we cannot read a lot of things, but if you notice, you may see a couple of patterns. First of all, okay, we see some numbers, a 2, 2, and 9, and 1. We have no idea what it is. Then we see something that's called 1F8B, some bytes, and then this repeats also here in, I don't know if you see my cursor, but it repeats down here in byte 50. So this starts to look like something. Maybe you don't know what is 1F8B. Does it mean anything to anyone? Yes. So we'll talk about what it is. Max said it's gzip. So if you see the distance between the first 1F8B and the second occurrence of 1F8B, and if you kind of measure the bytes, 1, 2, 3, 4, 5, you will see that it's 22. which is a big coincidence because we have the number 22 at the beginning of 32, 32 in hex, in ASCII is 22, like if you see on the right. Here it's 22. And then we have 91. And if you count from the second occurrence of 1F8B until the end, it's 91 bytes. So it looks like as a hypothesis that 22 may be the size of one part that starts with 1F8B, and 91 is kind of the size of the second part. So this is still a hypothesis. I don't know if it's true, but I'm assuming that this protocol has a length, some, I think a space, a zero, a null byte, another length, another null byte, and then two parts. Each one has the corresponding lengths. It's still, we don't know if it's true. So maybe in order to see some more information, we can just right-click on the bytes and copy the bytes as hex stream. Can you see? So copy bytes as hex stream. Right-click. And I will go to a nice tool that some of you already have used called CyberSef. And I will put my stream. I will try to paste. Oh, not the whole thing. Just a second. Copy the data. If you go to the data, it's probably easier. On the data, copy as hex stream, so you don't take the whole thing. And we can paste. So, for those that don't know CyberSef, some of you may have used it. It's a very handy tool that you can use in order to actually check data, modify. It has, for example, you can encode and decode in base64. You can create hexadecimal, from hexadecimal to other kind of to strings, or there is also encryption, public. There is a lot of operations that you can do over data or over files, and it can be very handy because right now, for example, we know that this bytes, the first one, the 32 is 22, then a null byte, and then 91, and these are kind of the lengths. So if I remove them, we get here a prompt. So if I remove the first 6 bytes and I only keep what starts from 1F8B, maybe, okay, let me do this. So if we only keep the one that starts from 1F8B, we see that actually CyberSef understood, and it says, oh, if you use the recipe called from hex, there is something there, and I can click and actually create it, and you see, okay, what it created was some gibberish. We don't know what this is. But again, if you click on the magic, it understands that it was gzip, as Max said. So if we click on the gzip, we have now two recipes, the hex and the gzip. And we see something that looks humanly readable, right? Like we see something that looks as an IP address. There are things that we don't know what they are. What is this? Can I not say what is this? Let me go. Okay, sorry, but this doesn't help. What is this? The green thing, what is it? The DHCP 83, 181. Anyone? What is this? What is the domain?
Is it like the local DHCP server got locked?
The internet says DHCP server.
No. Okay, let's look up. So this, and if you see this, this is the exact same address we have here. So basically, it's the reverse lookup of the IP that we're connecting. So it's basically it's a translation. If you do a quiz of this IP, you will get the DNS that resolves this IP. I don't know if I explained it well, but it's the reverse DNS, let's say. Anyway, so we have this line, right? We have a line that has some information, and it looks like our hypothesis was mostly correct for this line. Like, it looks like the strings, the lengths are correct, and it looks like we have gzip. So we are one step closer in understanding that this communication protocol, at least in some aspects, because you can look and see if this is happening in all the packets, at least in some packets, this communication protocol encrypts stuff obfuscates stuff by compressing, by gzip. And it follows a specific format that has an IP and a port, and some information that we don't know what it is, and the DNS, and okay, that's something. But maybe we just look at one packet, right? Does it apply to all the packets? And let me try to make this bigger. So can you check if this applies to other packets later down? We have a lot of them. It may or may not work, right? So we looked at packet 36, I think. No, it wasn't, yeah. Packet 36 was the first one, no, 36, this one. 36,908 was the first packet we looked. But there are plenty of packets that go this direction. I can help a little bit more, and I can put that we can only look at packets that have data, because if they don't even have data, then what's the point? So we can improve our filter a little bit. And let me see here. Oh, it's very hard when I increase the. Wireshark is killing me. Okay. So these are all the packets that have data. And we can see if we start scrolling that not everything looks like it has something that is actually similar. Like this doesn't, for example, look that it starts with some numbers. We look at the next one, the next one. Okay, this looks like something. With 110 and 103. I'm always looking at the ASCII part on the right side, right here, the 110 and the 13, to see if they start with bytes, and then if I see that there is a 1F8B after in the 7th byte, or in at least at the first 10 bytes. Okay, this follows the pattern. This doesn't. So you can start looking at packets and see, are there more? Or was it like a fluke, just one packet that was following this format and then everything else hidden? And if you look a little bit further, you'll see that the majority of the packets that have length that are, it's actually not very, it's like 100 or 200, less than 300 follows the format, but some of the bigger ones don't. So I would personally like to automate this. I don't want to look at one packet at a time. There is no point to look at Wireshark. So this is where we can start, for example, using some Python or some other code to automate the process. So I will go back to the document. And here is a time maybe that you can log into your Dockers. And if you are in the CTU, you just log into your Docker. And if you are in the Hacker Lab in SCL, please log into the reversing lab by SSH into this IP. And the MOOC students will always be working on this reversing lab. The CTU students on your Docker as you are, you don't need to do anything else. So let me log into my Hacker Lab. SSH. I need to start it. Yeah. And in CTU, let me see. I'm already there. Copy, before we start, it would be good to copy the files that we want to need for the class. And I will go to the reversing class, first example. And inside there, you should have the same pickup file. I'll do the same in SEL. Here. Plus, oh, okay. So, also if you are in SEL, you need to download the pickup file. I think we didn't want to package it in the Docker because it contains malware, and we didn't want to have malware in the published Docker in GitHub. So please run this curl command to download it on your computer, on your Docker. But the CTU students should have it, so it should be here for you. Okay, so let's start our Python and try to see what we can do. Yes, with this. Oh, before we do Python, we need to extract the fields. Okay, so in order to extract all the fields, and we do the same process we did on Wireshark, we're going to use tsark. Tsark is a command line equivalent of Wireshark. It uses exactly the same filtering syntax. And I think it's from the same group. I think they're very connected. But because it's command line, it allows to actually run command line tools and then automate some stuff. So we're going to run this command, and we're going to read the pickup file. We're going to specify that the output we want is the fields of the data, because you can have JSON, you can have different types of outputs. But here we care about exporting the fields. We're going to run the filter that we used in Wireshark. Here I added also the length to be less than 300, so we can discard the packets that are too big and maybe didn't follow the formatting. And -c means that from all the fields that Wireshark or tsark has, I only want the data field, so I don't care about the headers, I don't care about the TCP or IP. And we're going to run this and save the output in the small data log in a text file. So let's run this before we go to Python. Take a few seconds. And I will try to do this also in SEL. Okay, so you should have something that's called small data log. And if we do a less on this small data log, you will see the data. And if you remember, that was kind of, it looks like what we had on the Wireshark. It starts with 32, 32, 0, 39. And each line basically is, okay, maybe it's wrapped, but each line is one packet. The data of each packet that was for this specific TCP port 80,000, and it was length less than 300, based on the filter. So now we can start using Python to see how we can automate this. So let's start our Python and try to open the file. We call it small. I don't know why I'm not copying this. So with open, enter, and then you press tab because it's Python. And read its line and create an array of the log data will be an array that each line will be one line of data that we have. Okay, put it there. Enter, enter. So if we see, for example, the length of the log data, you should have something like 13,781 lines. So if we see the first one, which is the packet that we already, so this is how it looks. But if you see here, it has a new line character. So if I want to remove this, I will strip it. So if you do .strip, you get the new character. So now I can actually try to convert this from hex to kind of bytes. So I will use the bytes from hex. Oh, not this, not this. Copying and pasting is hard. So this is the bytes, the byte value, and if we actually take the first 2 bytes, 22, and if we want to make this, so this is how we can get the length, for example. So this is how we can automate the extraction of the length, the first 2 bytes that show that the length is 22. So we take the hexadecimal, we use the bytes from hex from Python, we convert this to a byte value, and the first 2 bytes, for example, is the length. So in order to continue and do the gzip, for example, I will convert the whole thing as I will remove the strip. I will remove the new line character completely, so I'm using to have a clean byte stream. And then we know that the first part is the part that starts from byte 6, because the first 6 bytes were length, null character, length, another null character, and then we have the 1F8B, right, which is the zip content. So I want to remove these first 6 bytes. So the first part of the byte stream is the one that starts from 6 and goes from 6 plus 22, which is the size that we extracted. So this is part 1. And then part 2 is the one that starts from the rest and just continues until the end. Okay, and now we need to do the gzip, right? We need to see, the reason I'm doing like that, I could give you the script, right? And you could write the script, but for me, you start testing and building it slowly, and then once you have a solution, okay, this is how I automate, then you go and write the script because you already have tested how you do the gzip and how it works, and in one packet, and then you can apply it in all the packets. So I can import gzip. And then I can say gzip decompress part 1. And we see this is the -1 that was at the beginning. And then when we decompress the part 2, we see the rest of the string. So this is what we were seeing in CyberCef. So now we have the pieces of Python, and we just need to put them together and go through for each line, do the same, and kind of output this unzipped stuff. Because then we'll automate this, we'll create some log, and then we can go through it. Or you can give it an LLM, or write another script to parse it. Then you can start automating once you have the process down. Is this clear? Do you want me to repeat something? Was it?
Questions? No questions from the internet? You got it? Everyone? Sure? This is the easy part.
He's joking. He's joking. He's joking. This process that we do now, it took them, because I didn't do it, Camilla was doing it with Sebastian. How much time did it take you to actually get into the point where you understand that this line does this? It may take weeks. Like you try stuff and you try stuff. Now we simplify, but it wasn't like you should understand this in 5 minutes. No, it's fine. I try to get you through the thought process, but I understand it's sometimes arbitrary. So you test stuff and you fail. You test, you try to automate, you fail, you see you don't get any results. And eventually, once you find it, things start falling together and you can get something to analyze. So
remember that we are used to encrypted protocols that we have no idea what's going on, but inside every one of these protocols, you need to transfer information, you need to acknowledge where the information is starting, where the information is ending. This is not magic, you need to say that. Maybe the length, maybe the type, so maybe the output. So if you have this in mind, you can start analyzing any binary protocol and try to figure out the pieces, right? If it's not encrypted. Yeah. And many that seems encrypted, they are not, they're just binary, and you can go right now and analyze, right?
So to make it easier, I have already the script that does this automation. We don't need to go through all this, but for example, here is the code that finds the sizes of each part, and then it just goes through. Again, we do the byte stream, and it finds the sizes and goes through each line for each line in the log data and does the same thing and just prints it. So we're gonna run this and we're gonna print it, and we're gonna take a look of what kind of things we see. So just run this, and I will give you some time to scroll up and down and tell me if you see stuff, because you're gonna see some stuff that you can read. Not everything is gonna be readable, but you see, for example, we see part one, this, and this is what we know. Then we see some stuff that are maybe weird. Then we see some other things that have info and all that. So take a few minutes with a less, go up and down and see what kind of information, like you see stuff that makes sense, like ping. What does this protocol doing? What is this communication doing? Just play with it. There's a lot of nice stuff in there. What? So, anything interesting?
So the internet says, ping packets looking through folders like the storage emulated 0 download or O download. Is this a phone it's looking through?
Yes, it's an Android phone. And you can see, for example, that it looks at some directories that I think that are Android. The storage emulated 0, I think it's the folder. One of them is the folder of the Android. For example, here it's a photo that it downloads. Yes, we see a ping. For example, this ping is probably some heartbeat to make sure that the rat is still running on the Android phone, and it tells the server, yeah, I'm still here, I'm still here. And it may be interesting to find how often this is, to see how often this communication is happening. For example, if we print also the timestamp, we would know how often this happens. Maybe it's interesting at some point. What else?
The repeating 21 YPCs 140. I don't know what it, because to me it seemed first that it could be some other type of heartbeat, but now if the heartbeat is made by the ping, it doesn't make much sense to me what it could be. That was too loud.
Sorry.
Yeah, so I already basically said it. I would be interested in what could be the 21 YPC 740, and it doesn't make much sense to me because it's repeated, it's sent often, and it seems like some kind of command, maybe.
Maybe. I would be interested to learn too, but right now from what we have, it's not clear what it is, because it's sent quite often, but then it stops, and it's not like the ping. I think the ping is more, it looks more periodic. So, but we don't know what it is at this point.
Oh, okay.
Anything else? So here in some of them, you see that there is some weird kind of things. I think this is the Android library, but doesn't matter right now. You see some method and then some delimiters, and then create, and then storage emulate file example. So you see this method and then something else, and method files, method create. So this looks like commands to me. Then you have method command, I think that was command, which is cp minus r. So copy something from this storage to this storage. So this method, this is how I think it passes the commands and the different things to do. What else? I have in the document some other things. Let's go. So we saw the method, we saw the ping, the files. At some point, I don't know if you saw it, what is this? Yes, it's geolocation. So it sends also the location where the user is right now. So that's also one of the commands. So another question for you. Did we manage to reverse all the packets? Like, did our script figure out everything? No. Other things, what else could we do? Okay, we found some stuff, but we don't have all the information about the traffic. We do have the malware, so one thing that we could do is actually try to reverse engineer the Android itself. And that's another class, we're not gonna go there, but it's possible to get some information from the Android. You can decompile it to Java for the most part, and then maybe we can answer some of the detailed questions like what is the YPC thing is. What else? We can look at the failed packets, why they failed, and maybe the bigger packets to try to see other kind of patterns. There's a lot of things. Anyway, in case you want to know exactly what the analysis found and some more information, you can go ahead and read the blog. But I think we will stop here unless there are some questions.
No, but the internet is putting the /storage emulated photo, blah, blah, and saying sending photos or
Yes.
what?
Yeah, this is the storage folder, I think, in the Android phones. So it can download all the phones, all the photos from the phone.
And remember, this is a real rat malware. This is not emulated, simulated. This is a real thing, right?
Okay. Any more questions before we go to a completely different chapter about GDB and assembly? Any comments? Was it interesting, or you think that this is very... Because some people find this very arbitrary. Like, you don't have instructions. Sometimes you do math, and if something is proven, it's proven, right? If it's code, if it runs, it runs. But the reversing sometimes requires guesswork. It's not always that you will find the answer. Maybe you do, maybe you don't. But you try stuff until you figure it out. And the rabbit hole may go really, really deeply. Okay, so let's move to a little bit of reminders about assembly and GDB, just to get your heads a little bit back to the last week course. Yeah, some of primers on assembly and x64 assembly. If you need them, just I cannot write anymore, apparently. So we're gonna see a bit of assembly. Some of the main registers that exist are RAX, RBX. Each of those usually has some specialized functions, but sometimes this is not always the case. For example, when you do some things like some I think subtraction or addition, usually the accumulator is the RAX. Some base pointers are usually on the RBX. The counters sometimes are RCX, but this is not always the case, and it's not necessarily 100% that will happen. We saw the RSP last week, and I think the RBP. One of the things that you need to know is that these are calling conventions. So when we will see in the assembly, we see the assembly of a function, at least in some calling convention, we use in order to pass the arguments, if the arguments are integers or even strings, which are pointers, which are integers, we use this sequence. Like the first one goes to RDI, the second to RSI, RDX, and so on. So if we have two arguments, RDI will have the first, and RSI will have the second. If there are some arguments that are floats, that's a little bit more rare. You're gonna see these registers. And another thing that we may see is that there are some registers that are non-volatile. That means that once you call a function,
the function itself need to preserve them. They cannot override them. So we will see what we do in order to keep their values, do our stuff, and then the function will restore the values before it returns. The rest can be overwritten, and then usually one thing that also is very useful to know is that the RAX usually has the return value of a function, or almost always. One other minor thing that you need to remember, or you will see definitely, is that if you see RAX, it means it's 64 bits, but if you see in the assembly EAX, it's going to be the 32-bit, the first 32-bit, the lower 32-bit. If it's 16-bit, it's going to be AX or AL. So you may see different names, but it's the same register, but only we'll look at a small part of the register, a sub-part of the register, or the whole thing. Very brief. Some example of commands, for example, when we want to move data from a register to another, or we use the move command. Yeah, okay. So when we want to move address pointers, we use a load effective address.
Question. So I'm not sure if it's a real question or not, but the internet asks, how do you know you reach your limit on the rabbit hole?
You don't. Actually, that is a problem. That more experienced, if you ask experienced reverser, and I'm not one of them, they will tell you that one of the hardest things to do is to know when to stop going down the rabbit hole. Like, I searched long enough, I didn't find anything, I need to go up and look at the bigger picture. Or you need a colleague or a friend to tell you, hey, you spent like 2 days on this, it doesn't go anywhere, let's look at something else and go back again. So that's a hard question to answer.
Sorry, and also you don't know if it's going to pay off, right? Sometimes you are 2-3 months reversing something, and then there is nothing, or it's impossible. You have no idea, right? That's the thrill of the undiscovered spaces, let's say.
True. Okay, some more commands. When we do addition, we use the add, push something on the stack, put on top. Oh,
sorry, another question. Somebody's putting something about the plugin, and then says fireworks from the capture 147.32.83.181. It's a command and control address?
The 147, one of them is
81.
Yeah, one of them is a command control address, and the other is the address of the phone on the network. Yes. Okay. Push, we saw it last week. You put something on the stack, on the top or on the bottom. Pop, you take it out of the stack, and then different types of jumps. Okay. So for the CTU students, please run, actually run this one, because we're going to use an extension that's called Jeff or Gef, which is some extended functionality on GDB to make it a little bit, I think, prettier and easier to see some things. So the SEL has it already, but for you guys and girls, please let me go out here and do this. I think I already have it, but not this. This bus thing. Okay, and to make sure that everything still works on your GDB, if you run this command, you should see something that prints the Python version. For those that don't know, GDB comes with Python, it has some Python capabilities, and we'll see that if you run the command py inside GDB, you can have actually a Python interpreter, and you can do some stuff, and yes, and this prints GDB and the Python version that the system, I think, has. And the next command, the GDB init, should have something like the screenshot. So if we do this, you should see something like that. So Gef or Jeff, I don't know how it's pronounced, is basically a Python script that provides extended functionality to GDB. So it's just you add some more functions. So when we are ready, I can do this on the SEL thing as well. Yes. So we are gonna go and look at some very, very simple C code. It has 2 functions. One is the main,
We set a variable equal to 5, and if the value of a equals to the return 5 function, which is this one, which basically does some things and then returns 5. If this equality holds, it will print hello world. If it doesn't, it will print nothing. And we can go to the directory there. Let me go here. And we can compile this. And I'll do it in the lab. So if you run it, you see that the function is called and you print hello world 5. It's hopefully not a very complicated thing, but it will serve us to, it will help us to actually see GDB a little bit, some functionality to refresh. So we're gonna run GDB with this hello world. Okay, let me go. So you see here that the prompt changed a little bit and has this gef or jef. It doesn't, otherwise the functionality is more or less the same. We can put a breakpoint in the main function with b main. We can look at our breakpoints by, say, info b, and we see that this is the address of the main function and the breakpoint. And we can run. And it will run until we reach the breakpoint. So here, okay, this looks a little bit more complicated. If I didn't have to do this zooming, you would see that the top part is the values of the register, then it shows the stack, and then the code. Let me zoom in so I can actually explain some things. So when you see the registers here, you see RAX, RBX, and the first value here is the value what is stored in the register at this moment. If what is stored in the register is a pointer to the memory, you will see also the value of what is in what the pointer points to. So the first one points to, I don't know, to this address in the main. The second one points to another pointer, which points to this, which is the name of our function. So Jeff has all these kind of hopefully helpful things that you can see, okay, this, for example, RDI is just an integer, it's a value. So you only has 0, 1, you know that's a value. But this is a pointer because it points to another thing. And it also dereferences and shows what it points to. We also see the flags. Then we see the stack. So remember that we said last week that the stack grows downwards. Okay, here in the view, it goes up. Like the stack is like pizza boxes. You add a number, it's one box. You add another, it's another box. You add another, it's another pizza box. But the addresses go down, if you see. So it grows downwards, but like mentally here as an image, imagine that it goes up. It's just that the addresses are decreasing as you go up. And you see in the stack, this is the address of the stack in the memory, and this is the content of the stack, the second column. And again, if it's another address, it's dereference. If it's a value, it's a value. And another thing that it's kind of interesting to see is that right now we just stopped at the main. Both the stack pointer and the RBP are pointing to the same place in the stack because we haven't started running anything. We didn't try to allocate any bytes. We didn't try to put anything inside the function. So right now it also shows us where these two pointers are looking at. Here is the code, the disassembly, some part, and here is where we break. The breakpoint is this red dot here. And we can run our commands here. As I was saying before, we can run Python, for example, with py. Okay, Control D. So let's start a little bit. We can look at the disassembly of the main with dsas, or you can start writing dsas and press enter, and it will tab and it will complete. So here is the code of the main function. And let's see what it corresponds to what. So we have some C function, we have it in the document. First of all, what does this sub RSP hex 10 is doing? We saw it last week. Yes, allocates 10 bytes on the stack. Congratulations. Okay, next. What can we see? Let's look at the C code, and if anyone can tell me what this command, where does this assembly instruction correspond to in the C? Move, blah blah blah, 5. This one. I'll show you the C code here. So move moves data from one register to another, or
We start by in A, where A is located.
exactly. So it's 5.
We store the value 5 in A, which is located at RBP minus 4.
Okay, so exactly that. So it corresponds to the value int a equals 5, and a is a local variable, so it's gonna be on the stack. That's why we say the assembly. It will be where the base pointer points minus 4, which is because the stack grows. Minus 4. So the value of the stack that is actually after where our base pointer is going to be 5. It's our first variable. Like we allocated some space on the stack, and the first one is actually this variable a that will get the value 5. What is this? Okay, that's hopefully more. Exactly. This is how you call. This is how assembly looks when you call basically the function that's in this address, but GDB already knows, and it's nice enough to tell us, okay, I know the name of the function, and I will give it to you. So we may not have had this, right? It depends on how you compile. If you put optimizations and some stuff, remove the symbols, you may not have the names of the functions. So you just have call and an address, and okay, you can jump, but you have to figure out what is this doing. But sometimes you can use GDB even when you have the source code as a developer, because you need to do some tracing and see if you have some memory leaks or something, and you use debugging together with your code and try to figure out some stuff. So you may or may not have this information. Okay, and I think we have another one. And the last one. What is the equivalent of this one? No, the answer was if it goes to reserve the memory for the main function address. No, it's a comparison assembly. So it compares two things. What are the things?
So this one compares the D word, which is double word. If we have it compares pointer and value in register EAX, and the register seems to be 64 bits, so the D word pointer must be 64-bit value at an address RDB.
Kind of, but not exactly. So first of all, D word is the 32-bit integer. It would be quad if it was 64.
When you select the text, it's harder to read.
Sorry. So when you see the brackets, it means the contents of where the RBP minus 4. So if before we saw that RBP minus 4 actually got the value 5. So this compares the value 5 with the contents of the EAX register. So basically, if we look at the code, okay, if you look at the whole assembly, but eventually this is actually EAX or RX has the return of the function. So basically, it's this one. It compares this. So if we see the okay, maybe it's easier if we see it in the disassembly. So here, this happens Where is it? It happens after we call return 5. So we call return 5, the return value of the function, the result, goes to the RAX or EAX register. So it compares the return value of the return 5 with the value 5 that we had on the stack. So it's where the if happens. So, okay, just a little bit of assembly. I will try to be more gentle. So, if we want to see, to go to the next instruction, right now we start at the main, where at the kind of top, we go to NI, who means next assembly instruction, but it doesn't get inside functions. So it just steps as we see the assembly. It will run, we did the push RBP and all that, the preamble that was, we did the push into the stack. The next one is gonna be the move. And then if we do an I again, it's gonna be the call, but it's not gonna go inside. If you wanna go inside, you do step, which is SI. But okay, we can do one more. We are before the return 5. So, so if we, okay, we can break here, although it doesn't really matter. But just to show you. So you can say I want to break to the return 5 because the debugger knows the name of the function, but you can also select you can say break to an address and say B star, which is a pointer to the address. And now if we do info the breakpoints, you see that we have, okay, we have 3 breakpoints. Okay, these are a little bit different, yeah, because when you say B and the name of the function, it actually goes beyond this. It points to here after the move, the push of the stack and all that. So, okay, that's why they're a little bit different. But in reality, if we do run, we'll hit the breakpoint 3. And yeah, also if you want to delete breakpoints, it doesn't really matter. So, let's say we want to change the flow. We know that if we run it as it is, it will print something. But we also want sometimes to change the flow of the execution. So we could, I will go back to this assemble, return 5. So this is the return 5. And let's say we here we move to the EX this kind of value. Let me see where I'm. Oh. We're looking for this. Okay, that's not there. Yes, it's here. Boom, boom. Okay, so we want to put a breakpoint here because we want to see what is the value of EAX that we're comparing to the string. So I'm gonna put a breakpoint before this compare. I'm gonna put here actually. Oh, what? Am I blind? Okay, I will run it again. Okay. I'm starting again. There's something. I mean the. I know what's happening. Okay, we run. We're in this, we're inside the return 5. And we want to stop here. Okay, let me see if I can do this. Is it possible that this is a problem of the Docker thing? Let me see. No, it's the wrong address. Okay, so we put a breakpoint there before this check. Oh no, I'm in the wrong place. Oh man. Okay. Next. finally. Okay, let's recap. Yes. Thank you. So inside the return 5, I want to put a breakpoint before actually we do the comparison. I put a little bit too early, but I think it's not a problem. I think. So let's do the next. Yes, I made a mistake. Oh, again, come on. Really? You would think. Continue. Okay, so let's go to return 5. I don't know what's happening. I don't know what's happening. I will do another next, and then I will do a step, and I will get into manually. Sorry, my breakpointers. It shows the breakpointer, the breakpoint here. It shows it. I don't know why it doesn't work. So, next. Okay. Next. Okay, finally I reached the point where I should have put the breakpoint. And so what I want to do actually is, let me explain, because I did not do this very well. I want to break before the comparison is happening, so I can change the register and so that you can kind of bypass the flow. So, yes. Failure. So, I will go back. So we are inside the return 5. You see here the stack, that the main that called the return 5. We're inside the return 5, and we want to put, okay, we want to see what is the value of RAX in right now in, oh. No. Ah. The document is wrong. Okay. So this comparison doesn't happen in the return 5, it happens outside. Is this a comparison we're looking before? Oh, sorry, internet, sorry people. I got confused by my own document. So, okay, we can get out. And okay, so this is, we are still inside the return 5. I will keep pressing. If you press enter, it executes the same. So if I next, we're moving and we're gonna go out. So we're eventually gonna go out of the return 5, I hope. Hopefully, soon. Okay. Disassemble the main. Okay. We are here. I want to put this finally. Okay. Easier. B. Okay, so recapping. I'm going to put a breakpoint after the return 5 to check what the return 5 function returned and check the value that it's there and see what our stack has and see if I can change it to actually not print the stuff that we want. So if I do continue, we are now at this breakpoint that I managed to save. EAX has a value 5, and yes, we can actually change. We can see what our stack has with this command. So the RBP-4 address is actually this address on the stack, and has the value 5. And I can now set this address. I can set the value 6, for example. So I can do set. Let me check. I need the pointer. And now if I press continue, we'll see that it will not print anything. Yes. So all of this to say that if you are running in GDB, you can actually change stuff. You can redirect the, and for example, maybe you don't know under which conditions something runs and goes towards a specific kind of flow of execution. You can just change some things and redirect the flow and see what happens. So you can try to understand why this happens and all that. It was supposed to be simpler than that. I'm apologizing for making it more complicated than it should be. And I think that it's time for our break. We can actually stop unless there are some questions. And yeah, I will do better.
Clear? Questions? No questions. Sure. Liars. Internet questions too? Okay, yeah. So we are back at 57, okay? Internet, go, take a break, get some water, get some sandwich, cheese fondue, whatever, and back in 10 minutes, okay? Are you okay with the window, people? Do we leave it open? Close, open, close, open? Yes, yes, I think so.
Yeah, just tell us when you are cold, right? And we can close the window or close it. Okay. Okay, let's start slowly with the second part. So our goal in the second and third parts is to diffuse a binary bomb. So that was the binary bomb was a program that was provided to the CMU students, the Carnegie Mellon. It's an exercise that it's for them. It has 6 phases. For each phase, you need to find out which string you need to input in order to diffuse the bomb. So, and it has different difficulties, and it's a C program that will get the binary. So if you go to your Dockers, we can run it a little bit to see what it does, to get a feeling. So make sure it's executable. Oh, we can see here. So you should have bomb64. If it's not executable, just to make sure that it is. With chmod. And let's say that we run it. So we'll get a message that says, you have 6 phases with which to blow yourself up. Have a nice day. Just run it and put stuff. Boom. Okay. So, okay. We can try to run the file command to see what type of file it is, just to get some information. We see that this is a type of ELF 64-bit LSB Pi executable, which is basically a Linux binary ELF. It's okay, least significant byte encoded. It's pi. Does anyone remember what pi means from last week? Very well, position dependent executable. Yes, and we see that it also links to the LD Linux library, blah blah blah. So, and it has debug info and it's not stripped. So we will see some information there. It's not compiled with all the the optimizations, and it's not trying to be extremely hard, but still it will be some work. Let's see. We can run the command strings to see all the printable strings that exist in the binary if you do this, and we can do more. We can see some stuff that are related to libc, some things that look like libc functions like fopen and puts and all that. Some other library stuff. Okay, some error messages, some things we cannot read. And then at the bottom, you can start seeing, okay, there is some strings here that look interesting. And okay, we don't have a lot more information. A lot of debugging and other printable characters. So in order for us to actually work on this, we will use IDA, which is a disassembler and decompiler, which hopefully you've already downloaded in your laptop. If not, you have to take the time and do it now. But download the file also locally to your laptop, the bomb. So you're going to be using IDA in your laptop because it runs in any operating system. But we're going to be running the binary in our kind of Linux Dockers, because I don't know if everyone has Linux, so we need to run it somewhere to see that we're doing it correctly. Okay? So please download it if you have it, and then open IDA and open the binary file. So, okay, I will do new. I will find the bomb file. Maybe I will not do it here. Okay, I will say reload. You will press OK or get all the default options in this, and in this also dwarf something. Just get the default, just press yes. And you will be greeted with this view, which is, okay, I have my mouse, and with control, if you have mouse, which is the graph view of the main function. So you see how the flow, okay, you don't see the details, but this is how the flow of execution, and you see that this is assembly. And if we look at the tab here, it's the IDA view. When we see IDA view, it's the assembly code, but it's in a graph. Like if there is an if statement, okay, with a jump, it may split. If there is a for loop, you will see a line with a for loop. But if you press space here, you will see the listing of the assembly as we did with disassemble in GDB. And if you press space again, you will go back to the graph. Other things that are interesting, you see on the left side where it says function name, up there, you see names of functions, sub 1, 2, 3, we don't know what that is. We see names in purple here these are the libc, the kind of function calls. You will see, if you know a little bit of C, you will see maybe functions you recognize. It's okay if you don't, it's fine. You can always find information how they work and what exactly do they do. Our main functions are functions that we're going to use from our binary. You see here, it's the main, phase 1, phase 2. We will see the details of those. It could have been that the binary could have been compiled in a way that these debug symbols do not exist. Then you would not see any of this. You would see sub 1 to 3, sub 1 to 4. And then you will have to go in and try to understand it and rename it and say, oh yeah, I think this function does this. But now at least we know that our main function is main, and then there are different phases. We will see how they are connected. Okay, so far? There are other interesting views. So there's a lot of views. For example, if you go to the view, open subviews, there are multiple things that you can look at. Here, for example, we have already the imports. So these imports are all the things that were imported from, I think, only from the libc. There is no other. But if we link it with a number of libraries, you will see here all the imported functions that the binary is using. And then exports are usually everything that is defined inside our binary. So the different functions and some variables and so on. So go back to view A. Now, magic. Press, when you are in IDA view A, let's say in the main, press F5. And ta-da! From assembly, we went to something that looks like C. It's not very good C, because I don't know if I mentioned it, when we do the disassembling and then the decompilation, it's not and one-to-one function. It's not a straightforward thing. You cannot necessarily recover all the information. So you get something that looks a lot like C, but it's not going to be 100% what the developer wrote as C. So you're going to see some weird things. There's a lot of assumptions, some comments that that IDA puts here where these are stored. Maybe they make, and it can make a mistake also. It doesn't mean that it's 100% correct, but at least we can see some things that I think is more readable if you don't know assembly very well or not very certain. At least this is a little bit more readable. For example, we see in the main that it's called with these three arguments that are very usual, like argc, which is how many arguments we pass when we run like bomb, and maybe you put some other parameters or not. argc has the number of arguments. So if it's only bomb, it's going to be 1. If it has some other values, it's going to be more than 1. argv is the values themselves. So when we run bomb64 blah, 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 argv will be an array that has the first thing is going to be bomb64, the second thing is going to be blah, 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 blah. Anyway, so this is standard main, and the NFP is not always used, but it points to environmental variables. Let's skip it for now. So we see here the first thing that the code does, it looks if the argument is 1. So if we run it without passing any other arguments, it will read from the standard input. So it expects input, that we saw, right? We run it, and it was expecting for us to put something, to type. Whatever we type, it's going to be written in this in file. If we had run it with argc, that it's more than 2, okay, different than 2, but if it's not 1 and it's different than 2, it means that it's like 3, 4, 5, it's anything. It will print the usage. And if we run it with exactly 1 extra argument, it will try to do fopen. Fopen means file open. So let's go back to see this in practice. So when we do bomb64, argc is 1, and argv only has this value. So here it expects us to write. If we do bomb64, la 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 la, doesn't matter. Here it tries to open a file. And it says, oh, I couldn't open this. This doesn't exist. And if we try to say 2 arguments extra, it says, no, this is how you should use it. You should run bomb64 and maybe optionally put an input file. Otherwise, so we either have to type the answer or we have to put it in a file, and we'll see how we put in the file to make our life easier later. But right now, we're going to run it, and we're going to try to guess what are the strings what we need to input to not blow up. So not to get the boom, but to move forward. Okay so far? So we saw this. So take a minute to see after this part. This is the, okay, let me close this to make it a little bit better, and let me increase this. So we saw this with the arguments, and then it starts initialize bomb, and it does certain things. Take a minute just to see a little bit of the structure. One thing, if you click on a function name, let's say initialize bomb, it will take you inside there. If you want to go back, you press escape. If you get lost, go to this function name and press main, and it will take you to the main, okay? Just, or ask. But try to look from the line 28 that says initialize bomb, a little bit of the, how does it look like, and if you kind of get a feeling of what it does, because it should be. Assuming that the names are correct, right? Because maybe the names are fake. So, any ideas? So what do you think about this code? The question is, what does the code do? What do you think about the general structure of the code? Do you think you get a feeling of what is expected?
Waiting for an input, and I just saw it compares the input, and this depends on the input. It will say something like this. Here we can see that we can pass phase 1 or either boom.
Okay, so let's go a little bit. Yes, that's actually the general gist. I think you can see it, but there are a lot of hidden things inside there. For example, there are some functions here that are not kind of visible immediately. So we will see. Let's go first to the initialize bomb. So initialize calls this signal, which is a libc kind of function. So usually when we don't know what it does, one of the things that the reversers are doing, either in Windows or in Linux, one of the things that you need to do is try to understand what are these arguments. So it has an argument that is 2 and another argument that's called sig handler. So okay, 2 is a number, but what does it mean? And then sig handler is what? We will see. So I put here the manual pages because your Dockers do not have the man page, so I put, but you can find them on the internet. I put here, you can ask an LLM if you want, but I put it here. So if you click here, you see that the signal function, it's a standard library C. It handles signals as usual, and it takes as argument a signal number, and this sig handler is a function. So how do we know that? What is the signal number? What does it do? There is another manual page. Okay, that's not that easy. And if you scroll down, this is what the signal number is. So it's the signal interrupt. So basically it's the control C. So this handler captures, if we press control C when we run the bomb, it captures and does something. What does it do? What the signal handler function does. So if we click on this function, yes. This is the function. So when the control C is pressed, this function is run. Oh, it says, oh, you think you can stop the bomb with control C, do you? And it does some sleep and all that. So if we do that, for example, we run the bomb, and you say, oh no, control C, I don't want to put anything. And it prints that, and it delays a little bit to annoy you, and a little bit more, and all that. But this how signal handle is used in C. So initialization does that. It's just the control C. It doesn't do anything more interesting. We can press escape to go back, and another escape to go back. So here the message we already seen, and here, okay, the first reads a line. Oh my God. Let me close all this. We saw this. And the read line, okay, we're not gonna go into that because I think it just reads a line from the standard input. We're gonna go directly to phase 1. So we're gonna give our input, and the line variable will have the input we gave, and we'll go to phase 1 and see how it's handled. And okay, we see here that there is another function called strings not equal. Okay, what does this do? Okay, that's a very convoluted way to look at it, but let's go to the assembly a little bit. Let me go to the assembly part. So, phase 1. And we'll go to the strings not equal. Click. Okay, so this is the assembly. And I know that in the C, okay, and we assume that strings not equal will probably compare the strings. But I'm going to show you a little bit of how the assembly looks, and not to actually get you more dizzy, but to see a little bit what is happening. And we're going to go to the C for the most part. So, yeah. So we should be here on the strings not equal part. Before we get there, okay, we can talk about this. So remember that I talked a little bit at the beginning that some registers are volatile and non-volatile. So for example, these registers are non-volatile. So why we push them? We push them on a stack to save them. Now we can use the registers and overwrite them, and then at the end of the function, we'll pop them on the stack. So this is why these pushes are happening. They're not relevant to our code in any way. It's just the preamble of the function, the calling convention. So we also saw that, said that the values of the input in the function come to the RDI and RSI registers. So we see here, we store the RDI to another register and the RSI to another register, and we call the string length. But what are these values, and how do we know what they are? So if we go back and press escape, we see that the RSI, if we press escape and go up, we see that RSI has this string. Because if you click here, this is a constant. And you see that it's in the data section, and it's just this string, I'm just a renegade hockey mom. So this is just a string that exists in the code. And it's in the RSI. And before that, if we go one kind of in the main function of the assembly, we see that RDI has the output of the readline function. So readline is called, it puts the output in the RAX, the result. We move it to the RDI, and then we call phase one. So RDI now has our input. And RSI has a string that it's on the code. And then we call the strings not equal, and the first thing that they do is they check the length of the strings. And they put the result into the first result into the R12 and the second result into the EDX. So basically we compare, the first part is comparing the strings. When you're going to compare the strings, you probably sometimes you compare the lengths first and say, okay, if the length is not the same, then why even look at it? So this is what this does, this first part. Clear? Questions? Or? Okay, so if this comparison does not work, we're gonna jump directly to the output, and that means that the strings are not gonna be equal. Before that, we see that the value of EAX, it has become 1, the default. And if we actually jump to the output now with the value 1, we will see that the bob will explode. And I will explain exactly why. Because if the output of EAX is 1, it has a value 1. And it runs this test EAX, which is a logical end. So 1, logical end 1, it's gonna be 1. So if this is not, that means that when I test it, the 0 flag is not gonna be on, so this is gonna actually go to explode. So if our function returns 1, the bob will explode. If it returns 0, we're gonna continue checking the next one. So here, let's say the comparison was okay and we moved on. So the next part here is to start comparing the two strings. And what do we do here? What the code does? It takes a byte from RBX, which actually had our string. Wait for me. So here we saw that RBX had the first string. Okay, so here, I don't want to show this bit to make your life complicated, just a little bit of the detail. But for example, here we see that it's a byte pointer. So the RDX has the whole string. It's an array of bytes, but we're only gonna get the first one because it's a pointer to the first kind of byte. And we move it to this EDX. And the first thing that it does this test DL. If this is 0, if it's a null, if for example the string is empty, it's going to be the null character. So if this doesn't pass, it will actually go and exit directly. So every time we want to compare the two strings, we compare until the string ends, and we have this null pointer at the end, null character at the end, and we know how to exit the comparison. If this doesn't happen, it will just start going through one by one. So we already have let me see how to do this. Test DL. Yeah, yeah. So you are where? Let me go. So if you are in phase 1, double click, and in the IW you're there. And then if you go to strings not equal and click, you get in there. No problem. It's a bit kind of, yeah. The thing is that it doesn't synchronize. So if you are in the pseudocode in the C and you click, the assembly doesn't go to the same place. So you go to the assembly and it's in a different function. So it's okay. Okay. So we tested that our first, one of the strings is not starting with a null pointer. So the next thing is to do is actually to have a loop that tests the whole string. So we already have that the DL has the first byte of one of the strings. Now we compare it with, okay, first we need a counter, an index. And this is where EAX comes from. We put the 0 value to the EAX for now. And we take the content of the RBP, which has the other string, plus RAX, which is 0. So basically, we take the first byte of the second string, and we compare it with the first byte of the first string. And if they're not the same, we exit. If they are the same, we add 1 to the counter. And we move the next byte to the X. We do the same over and over again. Does it make sense? A little bit. Do you have anything that I can clarify a little bit better? Because, yes.
Questions? We know it's hard. Need to understand.
Just remember that when you see the brackets, it's the content of the pointer. So the RBX points to something. It's an array, but it's the content of that specific value. And if you see RBP, for example, plus REX, it's RBP plus 1 is a pointer arithmetic. It's the pointer to the next element. So here REX is 0, so it's the first element, but after we add and we increase the counter, so for example here I could rename this, if I press N, I could say instead of REX, I could say counter. And sometimes you do that to make your life easier. So in this loop, this is a counter that starts from 0, and then we add 1, so we're going to look at the second byte, and then we're going to look at the third byte, and the fourth byte, until we get to the null pointer, and then it will exit. And we're testing this null pointer by this test here.
Clear? Questions? Any question is okay? Is valid? Like, what is EXX? What is RAX?
It's okay. And one last thing, if, for example, everything goes well, we see that before we return, we put 0 to EAX, which is our result. So when we end up outside, strings not equal have result equals 0, and this test will actually say, oh, logical end between two 0 values is 0, so I'm going to go this way. Because otherwise I would jump to explode Bob. So Bob is not going to explode, but basically we restore our stack pointer and we go back to the main function. So we're going out of the main function, and basically we are now, after we finished phase 1. Then there's phase diffused. I'm not going to go there. Okay, I can give you you will see that actually it has some secret phase that may be triggered and all that. I leave that to you if you want to do homework. Otherwise, if we manage to pass all the strings, it's going to be congratulations. But right now, it's not going to be successful for us. We just finished phase 1 and we see this string, right? So what is the string we need to put? Let's go back to the original question. Phase 1. What is the string that we need to put in order to get? Correct. So let's try. Let's try. So let's copy this. and try to run with the string. Okay. Woohoo. So phase 1 diffused. How about the next one? I don't know. I will put something. And we don't know. So in order to make our life easier, we will store this string. I think I have the command ready, to a file. So we don't have to copy this every time, but we're going to run the bomb with strings, and then we're going to keep adding on this file. So let me do this. So our bomb, or you should have a line with this, and if you run the bomb with the input, 64 input, you see that we passed already phase 1, and now we're ready for phase 2. So this cannot be, and this is where this argc equals 2 comes, that we saw that the arguments, when we have to pass a file, it will try to open it, and it will read one line and try to actually match it phase by phase. Okay. Phase 1 gone. And we have here the solution. Yeah. So we're going to start using the decompiler now to make it a little bit more manageable. So from, if you go to the phase 2 and F5, you should see something like that. It's phase 2 on the top. We have a function that's called read 6 numbers. Let me see, I think we talk about this a little bit.
The compilation can take time, right?
If for some reason we had some years ago the decompilation failed because it was a cloud decompilation. If it fails for anyone, we have the database that you can use to restore to get it, but I didn't see any complaints, so I'm hoping that it worked. So read 6 numbers. If we double click, we see that it calls scanf, which is a C function that reads input. It has this format that means that we're expecting 6 integers with spaces, and the A2 variable, the array, it will hold these numbers. So if you put less than or equal than 5, it's going to explode. So we need exactly 6, or more than 6, I would say. Yeah. So our next input will be 6 numbers separated by spaces. The first thing that it does, it says that, okay, V3 has our input. So maybe I can press N. If you click on a number, on a variable name, you can click N, and you can rename it. I will say input array just to make sure we know what we're looking at. So we look at the first element, and it says, if it's not 1, explode. So we know that the first element needs to be 1. What are the rest of them? What does this do? You select the variable. Let's say it was here. You click and select it. Click on it, and then you press N for name, and you can put any name you want. Sometimes you don't know what to put. You say maybe this. I think maybe this is something. You put something that you remember, and then if you verify that this is correct, you put a name. Just to make it readable, because sometimes you don't have. It's very convoluted here with V1, V5, V3. Okay, who knows? So, any ideas? Okay, I know that this is a little bit tricky. Please.
So the first value must be 1, and the other values must be the double of the previous value. So the correct sequence for it would be 1, 2, 4, 8, 16, 32.
Correct. Agreed. So Well done. So here, okay, so we see some weird things that the compilers do. For example, v1, it's a character pointer, it's a byte, but we don't want bytes, we have integers. So here it actually says, oh yeah, no, this was not a character, this is a D word, a pointer to an integer. So this is a very weird thing. And I take this, it's a pointer arithmetic, so I say where v1 is pointing, I take the pointer to the next element, and then I dereference and take the value inside there. So the value of the next element should be 2 times the value of the current element. Yeah, because, okay, maybe we didn't see this. So v1 basically points, it's the same as the input array. So maybe I should have named this input array. So basically it looks at its element, the next element, and says if the next element is not twice the previous one, then explode. And then it says v1 plus 4 because it's 4 bytes to get to the pointer to the next integer. This is like, why this is a character pointer and not an integer pointer, I don't know, this is a compiler thing. But in essence, we need to double, as our friend there said. And what else? Yeah, and this continues until we I think until we run out of elements, I think. Okay. Let's say we get there somewhere, somehow we manage to get into that. But let's say we don't want to bother our minds and we want to ask, our friends, AI, to do it for us. Let's see what the models will say, basically. So let's create a file called phase2. And I copy that, select the whole function, phase2, and copy it into the file. And let's ask our friend Clippy to tell us what this does. Just a note for the internet people, the model inside the SCL is not very good, so you're not going to get a good result. The better the model, the more they understand. But at least this one here, for the CTU students, the SESNet model, I think should tell us. So it's thinking. And I don't know if this was part of the training data somehow, or it knew, but at least it knows that this is a part of the challenge. The first number is 1, each subsequent number must be twice than this, and it even gives us the result. It also tells us that, okay, these are the stack canaries, which I didn't mention, but yeah. So sometimes, I'm not saying that they're always going to understand, sometimes they even understand assembly, but you can ask questions, like even if you have some assembly that you're not certain about and you ask. I tested a little bit Gemini and I think ChatGPT, and they were pretty good at explaining what these assembly instructions are doing and why they're doing it like that. And so they're not necessarily a bad thing. I think it can help a little bit if you get stuck into something. But okay, I'm happy. Let's copy this into our. First of all, let's try it. And let's put it here. Oh, not this. Okay. Oh, no. What? We don't need commas. Oh, silly LLM. It gave commas. We don't want commas. 1, 2, 4, 8, 16, 32. Woohoo! Okay, so now we can, oh yes, thank you. I think we can just echo this and append it to our string, our file, so we don't have to. So now our file should say bomb64 inputs, has 2 lines, and if we run it, it expects the third one. So far so good.
Questions? No questions from the internet, but results are there.
Okay, super. So let's go to phase 3. I'm going to get to phase 3. F5, make sure that you are in the decompiled. And you will see a very long switch. So firstly, we see that we get, the scanf is already there. Okay, sorry. It expects 2 integers with a space in between. So we need 2 numbers as input. And the first number is the V10, the other is V11. Okay, I can rename first, second. So we need a number that it's kind of the first, and we have some cases if the number is 1, 0, blah, 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 and it does some things. And in the end, it checks if the first is if it's larger than 5, and the second is different than this final number, explode. So we know that the first number needs to be less than 5. Otherwise, it will explode. So I'll give you some time to try to solve this yourselves. Maybe try some specific numbers, because here you know the first number is going to be either 0 or 1 or 3 or 4 or 5 or 6 or whatever. But it shouldn't be higher than 5. So try to figure out a pair of numbers that will work. You can do trial and error, right? You don't need, you can say, okay, if my first number is 2, this is 0, this is 0 plus this is, you can do the arithmetic, go to label 7, do that, it's kind of, try to follow. You can write Python, you can do it by hand, you can.
I have a question from the internet. Which will be a real case scenario, like a case of use of this, or some kind of workflow? Maybe it's a question for later on.
I'm not sure I understand.
Like a real case scenario that you reverse like this, like a use case of doing this, cybersecurity.
For example, we talked about at the beginning that if it's a malware file and you want to understand what it does, you will have to reverse engineer it and figure out what the code does, or parts of the code. Imagine a ransomware that encrypts some files. Maybe you want to decrypt to understand how the encryption works, to create a decryption tool to be able to pass, to decrypt the malware.
So I think that in cybersecurity, at least majority of the malware we know is reversed, like in this fashion, right? Like the malware creators are trying to hide their code, obfuscate, encrypt, polymorphism, whatever they're doing, and then analysts are trying to figure it out. So for a lot of analysts, a malware reverse can take months sometimes, right? Depends on the size and the things inside. And this is actually the main reason why you have antiviruses and they work, right? Because you have this issue. That is, I think, that the straightforward one. And then in your daily life, if you're attacked, sometimes you have binaries that are installed, and these binaries are completely unknown. Nobody knows them. This is very common. So sometimes you need to take a look very fast of what's going on, right? In our case, I think networking is the most common situation. We have a lot of IoT devices installed in the lab, and all those traffics are extremely simple binary that you can reverse and attack, and that's also something that you can do, right? Yeah.
Okay, do you have any results? Any numbers we can try? Did you try anything? Did you make it work? Did it work? Yeah. Nice. Yes. I mean, we can try them. You said 5 and minus 126, right? Yeah? Well done. Oh, it's Control C. I always fell for it. Yeah, I always fall for the Control C. Or, yeah, 4 and 0. Control. Very nice. So, I mean, how did you do it?
Is this Candy server or not?
Yes. He shared the answer for us with us.
Okay, so the first number needs to be less than 5. So I just tried 5 or less. So I just tried with 5. And if it's case 5, then the variable v5 is 0. Variable v6 is minus 126. Then it goes to label 10. V7 is 0 because it's minus 126 plus 126, and then it breaks, so it goes to the end, and V8 is 0 minus 126, so it's 5 and minus 126.
Super. Basically, you follow the logic of the case and all that. There is one other way to do it. If, for example, we didn't want to do all this, one way that you could do it is, let's say we put a random number on our file. And we run our beloved GDB. No. Wrong. Yes, again with the breakpoints. So here now we know we're going to go to phase 3. Okay. And we're going to run it with an input argument of the file. Okay, now we're already in phase 3. And if we do disassemble to see the function, we'll see here that, okay, there are 2 explode bombs that we, okay, there are a few explode bombs that we care about, but the one that we actually really care about is this one. We can put breakpoints in all of the, let me see, I'm correct. Yes, because this one is whether or not the scanf works. So we care about this kind of breakpoint, and we care about this comparison. So we're gonna put a breakpoint here, actually, or let me put here. Copy. Trust me, I know what I'm doing. Oh shit! Oh, no, I don't know what I'm doing. Okay, so we continue, I guess. Yes. So now we are here before the comparison. We can go one more. We are exactly the comparison, and we can see the value of the 2 elements. The EAX has the value 0, and our input, I claim it's going to be 100. We can see what RSP plus 4 has. So 64 hex is 100. If you don't believe me, we can do Python, and we can write the hex 64. It's 100. So 100 is the number we put on the text file, right? And 0 is the number that's expected. So here it will compare and it will blow because I put the wrong number. But if we want to, we know now that the correct number is 0 for a 0. But if we want, also we can actually set the value already. But what? What? Ah. Star. Okay, and if we continue, we got the halfway there. So if you don't want to do all the operations, and it's a very easy, it's a place where you can see just the compare, and it's just a number. You can always just put a breakpoint before the compare operator, see what it needs, and you get the solution. Sometimes it's a little bit like cheating, but it's not. So okay, let's. I think we can take a break here. Before we take a break, I will show the passcode for the mock people. And let me increase. I hope it's visible. And we'll take a break for 10 minutes and 55. Just a little bit. I hope you saw it.
I think they're not saying aloud technique. 4:55, we are back internet, okay? 10 minutes. Go get your asado out of the grill. I think they are asadoing all over the world.
Okay, let's do the final push. sorry, but okay, let's do the final push so we finish and be happy. So we finished the first 3 phases. Let's go to phase 4. Phase 4. Phase 4. Okay, so what we see first, scanf, we expect again 2 numbers. And then, okay, one of them is V2, I guess. Yes. V2 is the second number, and it has to be higher than E. And we call a function 4 with V2, 0, and 14. The output of this function needs to be different than 10. Okay. So, what is this function doing? Let's see. Any ideas? What is this thing? Okay, you can see that it takes 3 arguments. It says that this local variable takes this value based on the arguments, and then if this is bigger than that, we call function 4. So it's a recursive function, it calls itself, and changes the values as they go. And I don't even know if that is kind of what exactly this function does. You can start playing with numbers, but for me the easiest approach, what I would do and what I did initially, is to actually write a Python function and simulate what the function is doing, because it may not is even easy to actually recognize, even if it's a specific function. Maybe it's a binary search, maybe it does something specific, maybe it's something that we should recognize, but it's not necessarily, maybe it's an arbitrary recursive function. How do I know? But we do certain things. We see, for example, that the first one, the V3, as I said here from the code, has to be 10. So it has to be expect the results to be 10, otherwise it will explode. So we know one of the values, and we know the initial parameters, that's 0 and 14 of the function 4, and we need to actually find out the value of the second one. So we know one that it's 10, we know these 2 values of the func 4, and we need to find which V2 will give the result of the function to be equal with 10. True, that V2 is higher than E. So we know that's going to be higher than E, which is 14. We know that V3 is 10, because if it was not, it will explode. The if will kind of happen. It's an OR here. And then we know that function 4 needs to be the output, the final output needs to be 10, otherwise it will explode. So basically, for me, the easiest way to go about it is to write some Python that actually implement the function 4 and give it some inputs and find which input actually does this. And I already done this, but before going there, I was testing if, for example, the models will be able to do this. So you can create a file called phase4, and you can copy there both the initial function and the func4, so both of them. So the LLM can have the whole context. So if you do the phase4.c, we can copy here both the phase4 function and the func4, one after the other, so the model knows what func4 is doing. And then I ask the, what's the model in Cessnet? The code, the Quen coder. We ask this model with Clippy. First of all, what does the code do? And yes, it understands the same things as we do. It reads to integer, blah, 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 blah. And then I said, I think, write some Python code to find the solution. Let's see. So, okay, this is not exactly correct, though. It is close, but it's not correct. So it defines the function 4. This is correct, I think, according to the C code that we have. Let me check. A2 plus A2 equals A3 minus A2 divided by 2. I think this is correct. But then here it returns V3 plus function. I think, is this correct? Let me see. Let's see. Yeah. Plus equals function 4. I'm not so sure that this is correct. We can execute, can we? Okay, 310. Is this correct? I think not. We can try. Boom. 64 input. Oh, sorry, I need to fix this. So we had 4 and 0 for the previous phase, right? That was correct. And the LLM told us 3 and 10. Let's see, is this correct? Actually, it was correct. For the people that are doing the mock, the SEL model is not very strong, but I already have a phase for Python, so I can show you my code. So basically, yeah, we can implement the function from the C. It looks very similar to Python, and then try different numbers until the result is 10, and that's it. Sometimes you just need to write some Python code. You don't need to understand. You don't need to spend more energy if you can just find a faster way. Because the goal of reversing is not necessarily to understand 100% everything. It's actually to understand and answer the questions that you care about. If your question is, how do I pass this stage, you pass it any way you can. So, let me see. Let me see that it still works. Yeah. So we can add this to our bomb, 64 input. So it was 3 and 10. So we can move to the phase 5. Yeah. And because I want to give you a little bit more time on phase 5, I think it's more interesting, and as an example, and so phase 5. I will try to give you some information, and then again another 2 numbers. No. Oh, wait, phase 4. Yes, again 2 numbers. We check the first number. Okay, that's very weird way. The first thing that it does is that it masks this number with f, this logical end. So basically the number will never be beyond 15 hex. So it will never be, f is 1111, it's like 15 hex. So if it masks, everything else will become 0, and the value of v1, it will always be 15 or less. And if it's actually exactly 15, it goes to label 7, which explodes. So we know that the number v1 will never be, actually, it's very weird. The first number will never be more than 15 or 15 exactly. So what happens, I'll try to walk you through a little bit, and then I will leave you to try to see on your own. So we know the first number is not going to be 15, but it's going to be less than 15, from 0 to 14. There is a while loop, and what does it do? Okay, these variables are initialized to 0, this one is increased, and then v1, which has our value that we care about, is used as an index to an array. If we double-click the array, we go here, it's a constant array. Okay, it's an array that has 1, 2, 3, if you count it until here, until the 5, these 2 lines, this array contains 16 elements. And they have values from 0 to f. If you look, none of them is higher than f, than 15. And if you also look, you see that they have distinct values. None of them is equal to any other. Okay? Does it make sense? So, this v1 is used as an index to this array. So let's say v1 has the value 3. It doesn't matter. So array of the element 3, if I go here, is 0, 1, 2, 3 equals 7. So then v1 will get the value 7. In the next loop, it will be used, 7 will be used as an index. So it's going to be the array of index 7. 0, 1, 2, 3, 4, 5, 6, 7. So it becomes b. And it goes on and on in a loop. What else? How long does it go? Until v1 gets the value of 15. Once it gets the value of 15, so 15 is our final number. So we start with a number, we jump into the array from one index to another, and when we reach v1 has the value of 15, we stop the do while loop. Okay? And what happens here is, with this v2, we keep adding the numbers, so this v2 should be different. Oh, why is this v6? I think this is incorrect. Okay, I think this f5 was not. This is very weird. Let me see. So v2 actually, no, v2 is actually the second variable here. I don't know why this decompilation is so weird. v5 and v6 are the numbers that we got as input. v5 is the first input and v6 is the second. This decompilation is a little bit weird because I see in the document that here it's yeah, you see here, for some reason the decompilation like yesterday was showing v5 and v6 and now they don't exist in the code. But okay, trust me, v5 is the first input argument and v6 is the second number that we put. So in the end, we need this sum to be equal to the second number, and we need v3, this counter, to be exactly 15, because if they're not, we're going to explode. So the question to you is, what is v1 and what is this, the two input numbers, v5 and v6? And you can do this in a number of ways. You can use pen and paper and go through all the numbers. You can use Python, you can use DDB, you can code, you can ask the LLM. But there are some facts that the loop we know needs to be done 15 times, because otherwise the v3 needs to be 15, so it has to go through all the numbers from 0 to, it has to go through all the array. We need to know that we need to know the correct sum. That's the second question. We know that this V1 is used as an index, and we know that V1 cannot start from the 15. It has to end in the 15 because of this. So can you try and work out which is at least the first value? Where do we start in order to end up in 15? And I will put this in bold. These are the facts. Very weird.
So I have a question, but I'm not sure if I get it. So
Yeah.
the,
Please.
the question is, why Python? As an oriented
Ah.
object language or anything in particular?
Oh, for
There's
me, Python is because it's very easy to write and it's something I know. You can use whatever language you like, if whatever you're comfortable with. It doesn't matter.
Yeah, question for converting the C code into Python. Yeah, more
You
legible.
you could take the C code and write C code. It's just for me, Python it was easier to do, and also LLMs tend to do better in Python. But okay, yeah, that's a super valid comment. We could have used the C code as it is and just create a loop outside and run the function until we get a value. That is very true.
Yeah, but it's true that the majority of the code given to the LLMs to train is like that type of Python, I don't know,
Yes.
C++, I'm not sure.
And for me, it is because I'm more comfortable, right? It's faster for me to write Python than C. But okay, it's good. You could do it in Rust. So where do we need to start to end up in F? To end up here. Any takers? Again, the facts. It needs to be executed 15 times. The last value has to be F. We need to find where to start in order to end up in F. The code goes through all the elements of the array, because if it was a loop, we will kind of, we wouldn't reach F in 15 steps. It would have taken less steps to reach, so there is no loop. We have to go through all the elements. And I'll give you one more hint. If you continue and you don't stop the while, it will just keep on looping. If you allow it to run more than 15, in the next step from F, you're gonna go to the number that is in the index F in 15, and then you're gonna keep going to the next number, and you will do a loop because there's no way to get out of the loop. You have to go through all the elements again and again and again. It's a cycle. So, for me, the reasoning says that if the value that I need to actually need to go in order to find where should we go where should I start to get F, I would say that this is where F points. If I go to the index F, it's the 15th, it's the number 5. And I claim that if I start by 5, I will end up in F. I will go through all the numbers and I will end up in F. And then the next time from F, I will go back to 5 and I will run all through the numbers, all through the indices and all that. Because if this wasn't the case, we will have to go through fewer numbers. Actually, it's not going to be mathematically. The code doesn't make sense. Why it will loop? If here this while didn't say v1 different than 15, and if it allowed if it allowed v3 to be bigger. Imagine that it was a while true, and we allow v3 to be 100, and we run it 100 times. It will go through all the elements, and then we'll start going through again the same elements. Because it's kind of a cycle. One element points to the next points to the next, the next point to the next, and we end up in 15. But if we continue from 15, we go to 5, and then 5 goes there, we end up to 15. So it goes the same thing. So if you want to find where to start, you start from the element at 15 points. I mean, you can do it manually, and you can try every index to see if I start from index 0, where I'm going to end, if I start from index 1, where I'm going to end. And you will see that when you start from index 5, this is where you're going to end. But what is the second number? So the second number, you can believe me or not, but yeah, you can use GDB, you can find out multiple ways. But we also need the number that is the sum. So here when we go into the loop, we take a number from the array and we add it to v2. We start from 0 and we keep adding. And we want the second number to be this sum. What is the sum? What is this number, the second number?
It's some of the elements that we went through until the v1 was 15.
Okay.
Including the v1 equals 15.
Okay. So that sounds correct. What's the number? Okay. So if we say that at the beginning, when I first did it, I just summed all the numbers of the array, and the total is 120. It's 0 plus 1 plus 2 plus 15. So it's all the numbers. But this, we can try it. And actually, that was not correct. And the question is why?
Because it doesn't count the first one.
Exactly.
And the first one is 5.
Exactly. So
if
if you see the code here in the loop, v1 has the value, which is 5, and then it uses the v1 5 as an index, so it says array 5, it puts this v1, and it's the second number that starts getting added to the sum. So the number 5 is not added, so it's 115. And we can do this with GDB. I will skip this because I want to show you also a little bit of phase 6, and we're kind of getting closer to the end. But let's do this. Let me do 64 input, and I put 115. And we can try now. Yeah, and we see good work. And that is going to be phase 6, which is the last one. But you could do it again with GDB. You could just go to phase 5 and run it, and then try to see find the address before the explosion of the bomb and see what the register has as a value, and see that it's not 120, that it's 115, and just use this number. But the explanation is correct. We need to understand why this happens as well sometimes, and the correct value is 115. So phase 6. Okay, this is a little bit more complicated. Oof. Okay, this is very, very interesting. But let me do some renaming. So first of all, we have this function called read 6 numbers. Again, it's 6 numbers, one after the other with spaces. So we don't have to... I will rename this to input array, the V6, 16. Oh, come on. And okay, I'll do a little bit of the analysis before before we get to the deep end. So it goes. The input array has 6 numbers, and it tries to check if basically none of the numbers should be larger than no the first. Okay. So none of the numbers is actually higher than 5. Okay, I see that you see different things than me. Because I already renamed some stuff. Okay. So for you, this is probably some other value, right? It's not I, it's something else. I'm sorry. So this is probably some other value, R14 or something like that. And I rename it to I because it's an integer. So basically, here we see that it goes through the numbers, and it checks that the number -1, if it's larger than 5. So basically, each number should be less than 6. We have 6 numbers, all of them should be less than 6. And then it looks, it goes through all of them, and they should be different. So each number should be different than the input array, which also holds our number. So I'll give you these 2 things as conditions, that we have 6 numbers, they're from 1 to 6, and they're all different. Okay, this is where it becomes a little bit tricky, because it has to do with structures, and here we have to do a little bit of magic. So if we click on this node 1 structure, double click, we go somewhere in the code. That's a very weird thing. Here in the line where it's 12, if you press D 3 times, 1, 2, 3, and here 1, 2, 3. So this is a struct that has 3 elements. DD means 32-bit integers. So it has an integer that has a number, an integer that has another number, and DQ is the 64-bit. It's a pointer to node 2, which is another structure exactly down here. So again, 1, 2, 3, 1, 2, 3. So this another node 1 points to node 2. Node 2 points to node 3. Node 3 points to node 4. What is this? It's a linked list. So we have a structure that is a linked list. Each node points to another. We see that the interesting thing that it has an integer that has some value that we don't know what it is, and then the others are 1, 2, 3. So they look like indices or IDs, you would say. So, undo. 3, 2, 3. So one hypothesis was that this is how it looks like in C. So we have a value, and we have an ID, 1, 2, 3, 4, 5, 6. And then we have a pointer to a structure, to the next structure on the list. And if you would run it and see it on the debugger, you would see that the node 1, when we are loading in memory, the first one is a 212. We saw the value here in IDA. 212 hex, right? Then the second value on the next column is 1, 2, 3, 4, 5, 6. You see the IDs. And then the next 2 are 64-bit pointers, and you read first the rightmost, and then so you go 5, 5, 8, 8, 2, 11, 52, 10, which is the second line here. It's the address of the node 2. So you start from here, then here, because it's the endian mode that Martin was talking about last week. So this is how it looks in the memory. It's not important just visually to see when you load the thing in the memory. You see that there are kind of this how it looks. So in order for us to help a little bit of the analysis, one thing that we can do, let me go to the phase 6. We know that let me see. This V7, it's a node. It's a node type structure, but here V7 was assigned at the beginning a pointer to something. It doesn't help us. It doesn't give us any information. What you can do though in IDA, it's kind of you can define this structure and assign it to the variables because you have an idea that this is how it should look as C, and you can create a type and assign it. So if we go to the local types tab and we press insert or right click here and we say add type and we take our C code that we have before, this C code, we copy it and we tell IDA, oh, okay, create a structure named node with this type, and IDA is smart enough to understand the sizes of the variables and everything, and we press OK. We will see that create a new type, a new struct type. And if we go back to our code and we say, okay, I know that this where is it? Let me find it. This V7 variable is of this type. So you can say right click and say convert to struct pointer and select our node. You will see here that it understood, okay, this thing points to the next variable, which is a pointer. And we do the same also with V8 because I think we assign it as well to this type somewhere. Where is V8? There's a lot of things happening, and I will not kind of try to make you very, very bored, but we can assign V8 there. So there's a lot of things happening and a lot of structures and all that, but I want to actually point you to this interesting part. This do while loop. What does this do? So imagine that we have these 6 structures and 1 points to 2, 2 points to 3, 3 points, at least at the, if we don't do anything without giving any input. So what does this check do? How does the bomb explode? Exactly. So it says if the I'm going through. Yeah. It wants the values to be in decreasing order, because it says let's say I'm going through the linked list here, and if the value of the current node is less than the value of the next node, then explode. So that means that we have to go from the highest to the lowest. And here again, it's an assumption. You can try to follow the code, but let's say that this is correct. And we have here the values, which node, and we need to pass the IDs, because the IDs are from 1 to 6, right? So we know that we need to pass the correct order of structures, of nodes, to be correct. So which is the highest? We look at the highest values. The highest 393 hex, so it's 4. Which is next? Or, sorry, 5, so 387. So 5, the next one is 393, 4, 3, then 1, then 6, and then 2. So I claim that it could be 5, 4, 3, 1, 6, 2. That's my claim. And we can try. So we said 505 space 3 4 space 3 space 1 2 6 or 1 6 2 1 6 2. Woohoo! And that's it. We defuse the bomb. I know the last one was a little bit convoluted. The reason I want to show you was mostly to see that you can actually define your own types and you can assign to variables to make your life easier. We didn't look at the code very detailed, why this is working. It was a lot of assumptions and kind of guesswork. But in the end, it actually, this while loop and the assumption was correct. I don't know if you have any questions or you want to go through something else. Otherwise, I think that's it from me. Any questions from the internet? Or yes, please.
Just a quick question. When we saw the when we put the bomb in the, in this one, in the IDA, could we just skip to the address somehow? Like when we see there's a phase 1, phase 2, phase 3, could we just skip to the phase 6 immediately?
You could overwrite and jump to an address. Yes, that's possible. But then this will work on the debugger, but you will still not know the solution, right? If you need the solution, you will jump and you will see that you won. But
yeah, maybe if we saw like there is some like window of opportunity, so, and we saw that like it's a certain address, could we, when we are running it, the program, could we just skip like when we know the address? I don't know if it's a possibility that we know the address, but if there is a possibility to skip like over the code.
Yeah. In the debugger, since it's load and you know the memory, definitely you can see where the end, where it says congratulations, and you can find this before this value and say, okay, jump. You have to overwrite some other jump probably, and say, okay, if you find another JMP instruction that it's executed before any explosion, you can just overwrite it with your own, and and it's called patching. You can even patch the binary and always do this loop even outside the debugging, I think. I'm not sure if the ASLR and the PI and all that will actually allow you to do this. I think not. If there was no this position dependent issues and the randomization of the addresses, you could probably patch it with a fixed address, but I think only in the debugger you can do this right now, if it has all this.
Yeah, thank you.
Thanks.
Question from the internet. Is stepping in GDB and modifying a variable to bypass a check to get a congratulations message also considered a solution? Huh?
No. Yeah, that was similar to the previous question. Yes, I don't think so, because you don't know the actual solution. At least for this challenge, I think it's not a solution. Because you can always, even if it's a binary malware, and you can bypass the malicious part, but you don't know how it works. So it depends on your goal, I would say.
And also from me, like, you have the opportunity to analyze the binary now, but sometimes the real binary does not run in your computer. That's remotely on some server, so you're just analyzing here. So yes, you can bypass in your computer, but maybe the only thing you control in the real scenario is an input or a web name or your username. So, but you know that that's used later for something, right? That's the key. So you say, oh, I can give you only 5 numbers. That is, I don't know, my birthday in the web page. And that, you know, that goes into a binary, and now you know that how you can exploit, right? Yeah.
But as we saw, you can jump before some comparison that may give you some clue on what to put to find the correct input. That, I think, it's fair. I don't know for the CMU assignment, probably they will not allow it, but yeah. Anything else? Or we're gonna go to the assignment?
Yeah, finally we have the assignments back after 2 weeks. So basically you will be reversing. It will be 2-parter, each is 2 points. One will be the network reversing, like in the first part. The other one will be binary reversing. Take care, like in the second part, the flag won't be in the standard BSY brackets format, but you will see it on the CTFD as well. So once you reverse the binary, you will know what you need to put in the CTFD. And yeah, that's it. The deadline is by the end of the semester, as all of these assignments from 5 to 10. So yeah, that's it. Questions?
Questions?
And yeah, Pioneer prizes, of course.
Pioneer prizes!
Yeah, and please give us feedback and give me feedback. And tell us, yeah, if the class was interesting or not, if you would like us to change something, the way we teach it, and so on. Thank you.
Questions? No? Internet? Okay, so see you next time, people. Next time is in the room that we always have, 107, okay? Not here anymore. Internet is going to be for you the same too, okay? I think it was the same link. See you!